Okay, let us start this double webinar to be delivered by IE and TUC on optimized operation grids, and also the second will be integration and capabilities of various technologies for smart grids. We hope that more people will join during the seminar, which, as Laura said, is being recorded. There will be an opportunity for some questions at the end. So, up to you, Laura.
Okay, good. So, as I Lucioni, we will give, we'll take this webinar regarding optimized operation of smart grids. And these are the three main topics that we will talk about in this IA section of the first webinar. The first part is about the unstable production and consumption that characterize the smart grid, and that means also that there will be new actors in this scenario, for instance, storage systems and the prosumers. Then I'm going to give a brief description of what the market is proposing in terms of optimization, what I've seen so far from an industrial point of view, and also what are the what should be considering in the process of defining an optimization problem for for operation of smart grids. This is the scenario of the smart grid now. So we have on the left side, we have production, the energy production. That can be traditional, because we still have a traditional production of electrical energy. And then we have also renewable energy sources. Then on the right side, we have consumption. So we have industrial customers and we have residential customers. So we have these two main areas of consumption. The first thing is that renewable energy sources are very difficult to predict and to control. But however, there will be an increase of renewable energy sources in the future. For instance, photovoltaics, wind energy. So we cannot say, okay, they're difficult to control and to forecast, so we are not going to use that. It's impossible to think like that. So renewable energy sources are going to be used more and more in the future, but they're tricky. They're very tricky. On the other side, there are consumption, customer. We don't know exactly the consumption. I mean, it is a bit tricky to forecast loads for industrial and residential consumptions. But at the same time, there's also another scenario that now consumers can also produce energy, because they could have PV rooftop installation. So we have these prosumers. There's not only a simple customer, but there is a customer who is also producing energy. And the very important thing is also the grid. Now the grid has to be stable. We must maintain 50 Hz for the grid frequency. So we need to balance consumption and production. But if you see that from one side you cannot forecast and control the production because it's renewable energy sources, and the other side you cannot predict with high precision the consumption, and also you have consumers that can also produce energy, you can understand that the stability of the grid that must be guaranteed. It is a very tricky situation. There's also a new actor in this scenario, that is storage system. Now energy, I mean, we are used so far to have a flux of energy, like from production to consumption. Now we have a sort of lung in the middle, so we can produce energy, we can store it and take it and keep it, take it whenever we need. So there's a new actor also to include in this scenario. So smart grid is something that is completely different from the scenario of energy that we have seen so far. That means that we need to consider this new situation and to analyze all the actors and all the tricky situations that we need to face. So why is it important, this operation part in the operation of smart grid? As I said before, the difficulty in planning in advance the production and consumption. Renewable energy sources, loads, it is difficult to forecast in advance. That means that it is very difficult to plan and to control in advance the generation and the consumption of electrical energy. But we need to balance consumption and production for the grid stability that must be guaranteed. And also we have this new actor, the storage system. So not only producing and consuming energy, but storing battery, thermal storage, or hydro storage. Still, it's a new actor of this storage system. Another key factor of this optimized operation is that we are having systems and assets connected to a microgrid that have different dynamics. For instance, if you consider to a lithium battery, it is very fast. The dynamic is very fast. But if you consider to an industrial consumer that is producing something linked to iron, for instance, the dynamics are very slow. But you need to control all these systems. So you are linking and connecting and controlling systems with different dynamics, and you need to include all of this. The same is for time scales, because some system has a granularity of 1 second, others of 1 hour, but you need to include all these consideration, all these constraints in the optimization problem. And also, the number of systems that a smart grid has, it's a growing number. It might be 10, it might be 100, it might be 10,000. So you have a growing number of assets that you are connected to a smart grid. That means that all this consideration, you have to have an optimized operation of the microgrid, in idea that we have this multiple system that must be controlled and coordinated through the optimization-based control strategy. So this is why we need optimization for controlling and coordinating all the assets in smart grid. So far, what have we seen from industrial point of view? What is happening? What the market is proposing from an optimization point of view? I've been in a fair 2 weeks ago in Germany. So this is there was the focus on optimization. So many companies that were proposing optimization-based product, and this is the main area that I've seen there at the fair, and also that I've seen so far working in the company. The first area where people are focusing a lot on optimization is, of course, trading, because they see the highest revenues, because trading and bidding energy based on a pure financial optimization based on the market price, that is the first area of optimization. Why is it related to smart grid? Because you are trading energy produced or consumed by assets in a microgrid. So that's why trading is still connected to smart grid. Then it is EMS, so the energy management system. You can have it at the building level. You can have it at the grid level. That means that you can control the lighting system in a building, you can control the shading in a building, but at the same time you can control PV production of various buildings that you have connected in a grid, in a smart grid. It has to be said that so far the EMS that you find on the market, they have a very basic optimization strategy already implemented. Then it depends on the company. Some of them, they're like, this is the product that cannot be customized at all, and you take it as it is. Few companies, mostly startup or very small company, they enable you to change or to customize a bit the optimization problem. But there's still, usually there's still a constraint on the number of assets that you can control or that you can include in the optimization problem as variables and as constraints too. Another part is an embedded controller. What I've seen so far is more predictive control installed. So the idea is that you have this optimization problem. So but the constraint matrix of the optimization problem has a specific structure, and this embedded controller defines and chooses the best solver based on the constraint matrix. The only idea to maximize costs, maximize revenues, and minimize computational time, because controlling smart grids is going to happen real time. So you need to have an optimal solution in a reasonable computational time, and so there's also this hard coding area of optimization applied to smart grids. We have also seen that companies like utilities and are focusing a lot on optimization for controlling the microgrids, and so they're doing that by creating dedicated advanced controlled units. And there the focus is only related to optimization. But what are going to be the key for optimized operation in smart grid? Flexibility, modularity, because it's not that the smart grid has a determined number of assets and that's going to be unchanged forever. That means that we will need to add new assets, a new system in a smart grid, as we will need to remove old ones. And that can be done easily. Also in the control system, we need to be able to add the constraints and variable easily, and so flexibility and modularity are going to be crucial. As well also the integration with the market. We all know that people are willing to invest money in something if they have high revenues on that. That means that they have to earn money from that, and so the integration with the markets by trading, bidding, that has to be included in the optimization system. And this, of course, is strictly related also to the forecasting part, because so also forecasting are going to be crucial and very important in the optimization process. What can we optimize? Let's say I have divided these two areas. The grid level may be most related to work package 4 and 5, but the building level is mostly related to work package 3. So at grid level, usually there are some grid services. So for regulation, primary regulation or secondary regulation, so there are these grid services to balance the consumption and production, and the main idea is to keep the grid frequency at the 50 Hz. You see now in UK, for instance, the National Grid has issued many tenders. One last year, a new one should be issued soon for frequency response. And they have required storage, for instance, also lithium storage, to provide the enhanced frequency response was in that case, but still it's to regulate the grid by using a storage system. It might be lithium or hydro storage, but still it's something that you can do that by optimizing all the assets that you have, by minimizing the spread from the 50 Hz, and by control the assets that you have. At the grid level, at the same time, you can store renewable energy, because if you have a wind plant, let's say onshore wind plant, and or also PV plants, and at that moment the grid doesn't need that energy that you are producing, then you can store it in a storage system, and then provided it to the grid, withdraw it to the grid whenever it is necessary, with the goal of keep the grid frequency at 50 Hz. At the building level, what can be done from an optimization point of view? We can coordinate the production and consumption with an idea to take it from the grid when the market prices are low, and withdraw it to the grid when they can pay us more. That is the idea. So, for instance, if you have a PV rooftop installation, you can decide to use the energy that you are producing during the day or whenever the energy is expensive to buy. And then you can actually sell it to the grid when you don't need it, and when the grid is paying you more to do that. At the same time, you can optimize by reducing the energy consumption of the building, and so also reducing peaks, because you know that when you have peaks in consumption, actually you pay a lot to the national system, because you are creating an imbalance to the grid. So in order to reduce these peaks, actually you can optimize it by shifting loads or by using energy that you have stored somewhere, but still at optimization level. The same, so it's with the storing the energy also at the building level that can be done if you have electrical storage or also thermal storage. For instance, what we are doing here in Leaf Lab with Angeliki is to store the renewable energy that we are producing during the weekends, because we don't need it. Our buildings are closed, and then we can use this energy that is stored in a thermal storage during the weekdays when the buildings are actually working, functional. But all these activities, of course, there are many others, but these activities, these are an example of what actually optimization can be used for. How can we optimize the feature of optimal operation of smart grids? We need to include all the dynamics related to market, to the asset that we are controlling, and to the grid, of course. We need to include updated input whenever they are available. For instance, if we have a moving window for a closing moving window for the market, we need to include updated market price whenever it is possible, because they help to have an optimal solution to the problem that is really feasible to the current situation. Also, usually optimization might be required to be done on different time scales. If you have intraday market, for instance, in some countries in Europe, it closes 1 hour before delivery, while the balancing market closes 30 minutes before delivery. So if you are optimizing by considering these two market prices, that means that you need to optimize some variables with a granularity of 1 hour, other variables with the granularity of 30 minutes. And these are all considerations that should be included during the process of defining and designing an optimization problem. Also, the input the control signal that the optimization control system provides to the asset must consider the asset dynamic, because if you have, for instance, an asset that has a certain dynamic, for instance, once a diesel generator, for instance, you cannot decide 1 hour to switch it on and then off immediately after. It doesn't make any sense. So you know that once some assets, when they're on, when they are switched on, they must be operating for a fixed number of hours. So these are constraints that must be included in the optimization problem. A key part also in the design phase is the computational time. Sometimes we must give up on the optimal solution, on the perfect model also, because maybe suboptimality is acceptable, because otherwise if you're looking for optimal solution, then it's going to take too much time, and that cannot be accepted. Because you see, if you go to a customer and you say, look, I'm going to provide you energy, but wait a bit, because my control system is not giving me the right solution now, so wait a bit. It's not going to accept that. The reliability of the system, the reliability of the smart grid is very important and must be guaranteed. At the same time, models and the variables that we are using for optimization, we all thinking to go with the linear model and real variables, but sometimes that doesn't reflect the reality. So there are some assets that are not linear, and they require the mixed integer problem or integer variables, and that must be considered in the design of the optimization problem. Modularity and flexibility again. We must be able to easily add and remove assets and constraints from the optimization problem. Reliability must be guaranteed no matter what, must be provided to the customer, and the control system must take care of this part. There's also another few considerations to have, also related to a fully decentralized version, a centralized control strategy. That means that you can decide to control all the assets of the microgrid in a fully decentralized way. That means that you do not have a master control system, but you have a set of decentralized controllers. That can be done. Or you have a master that controls all the assets in a fully centralized strategy. It depends on the number of assets. It's still an ongoing debate in the academia, but still there are these two also areas to consider in designing an optimization control system for smart grid. That was an example that we have made here in Loccioni, for instance, and just to show how actually you can integrate the market. So here we were in the optimization module that we have developed internally. We were taking a real-time price from the energy market, updated every 1 hour. And then we were forecasting the customer imbalance volumes, and also we were forecasting the balancing market prices every 30 minutes. So the idea here was to provide an optimal control signal to the assets that we were controlling, and also information to traders. That means that we were not actually simply controlling the battery, but we were providing information to traders, something like, okay, if you bid this amount of energy now, you're going to earn X euro, but if you're going to do that in 1 hour, our forecast suggests that you might earn something more or something less. So the final decision was taken by the traders. And that's also a key part of smart grid. I'm going to talk about it in the next webinar, because humans and the interaction with humans must be guaranteed and taken into consideration when designing the control system for a smart grid. So the conclusion is that, okay, optimization is very important, and at the same time, reliability and stability must be guaranteed. At the same time, fast computation, modularity, and flexibility. Academia is focusing a lot on this research area of optimization. The drawback of that is sometimes we tend to have a too complicated problem and that requires too many information at the beginning that customers simply do not have. They don't have the faintest idea of how to take this information, and they are not willing to look for this information, especially when they don't see an immediate return of investment of that. So I suggest as academia and the industry, also through smart gems, we should find an efficient way to design and define an optimization control system for smart grid, but they're very easy to start and to implement. At the same time, they should be efficient, of course, and that might be a bit tricky. And so this is done from IAF. So I think I should make Denia the...
Yes, thank you, Laura. I think I am the presenter now.
Good.
Thank you very much. So
welcome.
I will continue this presentation by focusing on demand response as a prominent field in the smart grid concept, in the sense that it is a valuable tool and attracts a lot of interest from stakeholders in the policy and market side, and of course in research foundations. We will see that quite a lot are being done in this direction, with some of the EU member states having made considerable progress and others still lagging behind. The aim of this part of the webinar is to provide the wide general picture about demand response and not a deep insight into the electrical energy market. as in Smart Gems we are more focused on the demand side management, but I think that it is important at the same time we acknowledge why demand response is valuable for all key market players. And questions like what is demand response and why demand response will be answered before going through some of the EU regulatory reforms and how they are gradually being reflected in various legislative acts. So primarily we will try to draw upon the actual progress of demand response in terms of the technical framework, but also we will describe some of the new business entities already developed in some countries. So demand response is a program of incentives or a way or a tool to induce changes in electric consumption patterns by end users. And this is important because it could induce lower electricity use at times of high market prices or when grid is at stress. And there are quite a few challenges ahead for the smart grid, and one of them is the penetration of electric vehicles, which, according to some estimates, could increase the peak demand by up to 40%. There is electrification of heat, which is another critical issue, and of course, increasing renewable energy sources engagement, and this creates volatility that utilities should deal with. Unfortunately, here this graph is not working properly, but what I meant to show you is that as this is a curve, the net load curve for California in January 2012, we could see the difference between forecasted load and expected electricity production from variable generation resources. So in other words, this curve shows what the independent service operator must follow during the day, and it can be divided as you see in 4 segments, starting from left to right. The first segment is an upward ramp of about 8,000 megawatts, and it occurs in the morning starting around 4 a.m. As people get up and prepare for their daily schedule, and goes until 7 o'clock. And then we have the second segment in the downward direction, which is sometimes described as the belly of the duck. The first segment is the tail of the duck, the second is the belly of the duck, and as we see, we have this in a downward direction, and it takes place after the sun comes up, just after 7 a.m. in the morning, when conventional generation is replaced by supply from solar generation resources. And then we have the third segment there, starting around 4 p.m. in the afternoon, and this is where solar generation gradually goes to zero, and the ISO, the Independent Service Operator of California, must dispatch resources to meet this third and sharp daily ramp, or as otherwise called the duck's neck. The fourth segment is a decrease in the demand, where the operator must reduce or shut down generation to meet the final downward ramp. And this is another example from spring this time, and again we see that according to the forecasts going down to 2020, there will be a very high performance, a very high gap that the operator needs to fulfill as renewable sources are being increasingly connected into the grid. So the belly of the duck is, let's say, goes down to a lower point. So this ramp, then the second ramp in the upward direction becomes wider. So in this case, I'm not sure if the peak increase due to electric vehicles has been taken into account, but this is something that could even make this gap even higher in the future. This is another graph, and the main difference in this graph compared to the previous ones is that we're interested in the behavior of the consumers. So this is a peak time rebate, which is a program rewarding customers who reduce electrical consumption during peak times. And participants who in this case are residential customers are rewarded based on the sum of the kilowatt hours reduced multiplied by a rebate rate in dollars per kilowatt hour. And the graph illustrates one event day where the event, as the dust lines indicate, begins at 3 p.m. in the afternoon and concludes at 9 in the evening. This was a part of a pilot project which involved control groups. So we see two lines, and the blue line is for baseline group, and these people were not notified of the demand response event. And in the red line, we can see the collective power demand from the event group, and we can see that there is a clear difference during the event hours between the two groups, with the gap being maintained throughout the 6-hour event. In this particular case, kilowatt impacts for residential customers, the reduction of demand for residential customers was estimated between 0.2 kilowatts to 0.5 kilowatts per hour per participant. So one critical remark here is that demand response can be effective provided that participants are adequately informed and trained. And again, demand response events are characterized by different parameters such as start time, duration, nature, etc. And this is very important information that must be forwarded to the consumer. Results should also be clear to the consumer for them to see how they can benefit from participating in such events. And there is a notion that supports consumers can be increasingly involved if they are engaged in the kind of game fashion by having competitions between different buildings, and this is another important parameter which could be addressed in the future. In terms of the various or the main, let's say, different types of demand response, we have explicit demand response, where demand competes directly with supply in the markets through the services of aggregators, or in the case of single large consumers. And we have implicit demand response, where consumers are exposed in time-varying electricity prices and react to price differences depending on their own capabilities. In terms of policies related to demand response, it is important to note that the European Union has undertaken a proactive role in supporting member states to make steps ultimately leading to the implementation of demand response by addressing key issues and how energy markets should operate, by funding projects to minimize risks and lower the barriers for key market players or new entrants to invest time and resources and make the next step forward by monitoring and publishing progress of all member states regarding the opening of their markets to demand response, providing a valuable tool for knowledge exchange and strategic directions for member states to harmonize their regulations and incentivize change. And now, this is from the Energy Efficiency Directive. We see that there are specific clauses to ensure removal of barriers for demand response, allow retailers improve consumer participation in system efficiency, including demand response, that member states should ensure national regulatory authorities encourage demand-side resources, such as demand response, to participate alongside supply in wholesale and retail markets. Transmission system operators and distribution system operators treat demand response in a non-discriminatory manner, etc. There's a lot of information there. And in overall, we can see that the European Union is asking member states to authorize demand response, allowing consumers compete alongside generation in all markets, enable aggregation in all markets, and adjust technical modalities for demand response to be widely adapted. The role of aggregator is very important. The aggregator is a service provider who operates a set of demand facilities in order to sell pools of electric loads as single units in electricity markets. It represents a new role in European electricity markets, but is well established in the USA, Australia, South Korea, and Japan. And here I would like to talk about a little about the Open Automated Demand Response Framework, which is a standard framework developed for communicating demand response events between the utility and downstream entities, such as resources, using equipment that facilitate communication exchange. So some basic definitions which are being used in this framework. The Demand Response Program Party, of course, is the entity responsible for the grid infrastructure and for managing demand response programs. We have the aggregator that we just explained a minute ago. We have the resources, which is the entity enrolled into the DR program, and the assets, which are the physical systems or loads behind resources. In this effort to standardize, let's say, communication for demand response operations, various program types have been identified, such as critical peak pricing, capacity bidding program, thermostat program, or direct load control, fast DR dispatch, which is about customers' response in emergency events, electric vehicle programs, and distributed energy resources programs. And of course, the most fundamental entity for a utility to interact with is the resource, which could either be a single customer or a collection of customer loads, or even a thermostat. And this is a simple deployment scenario between the Demand Response Program Party and the Resource Party. So we have the Resource Party responsible for enrolling its own resources into the Demand Response Program, and the grid infrastructure then, via a communication node, which here is called VTN, Virtual Transfer Node, interacts with another communication node that resides in the demand side infrastructure. And examples of this scenario would include commercial and industrial buildings that may install a gateway, and when a signal is received, then it's simply being translated into some other protocol and forwards to the load controllers, to the building management system, which is being forwarded to the load controllers, the building management system, or the energy management system. Here we can see another scenario with the main difference being that there are multiple VENs, multiple communication nodes associated at the demand side infrastructure with a single compound resource comprised of multiple assets with their own load controllers. And this scenario exists in order to facilitate demand side infrastructures that have compound resources but do not have a centralized energy management system. And examples might include buildings with different load controllers on each floor, but no centralized building management system, or campuses with different controllers in each building, but no campus-wide controller. Another scenario here where we have an intermediary facilitating interactions between the demand response program party and the resources. And here the intermediary works on behalf of the resource party to help them manage their resources. But the resource parties have direct relationships with the demand response program party, and they enroll again their own resources into the demand response program. The role of the intermediary party is to act as an actuator for all related interactions, and the VN is instantiated within the facilitator. Such an infrastructure is often cloud-based and offered to the resource parties as software as a service. And examples in this scenario include vendors that manage facilities for large commercial chains, industrial control intermediaries, energy service companies, or cloud-based appliance and device management systems. In this scenario, we have an aggregator, and in this case, the aggregator is linked to the demand response program party instead of the resource, as we saw in the previous scenario. So the aggregator aggregates multiple customer assets into a single resource, and it enrolls those into the demand response program. The demand response program party does not have visibility into the individual assets that the aggregator is managing. Okay, as a conclusion, demand response offers the technical and regulatory framework for higher efficiency, inclusive participation, and operational transparency. And there is a lot being done in this direction. Research, innovative products, market-oriented efforts, and targeted policies which gradually drive electricity markets closer to more elaborate and wide-scale demand response in the foreseeable future. This is where my presentation ends. So, Laura, I think the floor is again
okay. Yep.
With you.
Mm-hmm.
Yes, thank you very much for the presentation.
Thank you.
I was wondering, I mean, we have got a few people that they have joined us in the meantime. And of course, as usual, if you miss some of the presentation,
yes. Hello.
It will be available afterwards. Should we ask for any questions now or leave it for the end, maybe? Maybe leave
Hello,
it
sorry,
for...
I lost you. Hello?
Shall we have a question now? because maybe I forgot.
It's okay for me. It's up to you.
Yes, maybe we have. We got a message from Pietro, idea that they cannot ask any questions because they don't have the microphone. But mostly other people, they are connected with microphones. So if there are any questions at the first presentation, now it's the time to ask them. It seems there is nothing at the moment. So we can leave it for later because there is quite a lot to digest, and perhaps, Laura, we can continue with the next presentation and then ask some of the questions, if there are any, later, or they can follow after the webinar.
Okay.
It's yours. Yeah.
Okay, thanks again. Thank you very much. So the second webinar will be about the integration capabilities of value technologies for smart grid. And this is what we are going to illustrate in this webinar. First of all, what should we integrate in smart grid, in a microgrid, in a smart grid? And I have defined three main areas: the communication, the control, and the human interaction part. These three main areas, and then the conclusion at the end. And as a case study, we are going to refer to the microgrid that we have here in Lucioni. So let's say that these three areas are related to the microgrid that we have here. So what are the main part of a microgrid of a smart grid? And so far I've thought about this main group. So we have photovoltaics, we have local management systems that can be at the building level, or it can be either at the asset level, for instance, the battery management system. We have storage, we have some extra assets that I haven't mentioned in this group. We have buildings, we have meters, and we have also actuators to actually make possible that the signal that we send to the asset, it's implemented, it's done. And then we have a control system. All these assets, so all these parts, all these components of a smart grid, how they can be integrated? They can be integrated via hardware. That means that usually to connect, to plug different systems, we must satisfy standards and certification that they are either defined international level, or they are defined at the country, even at the region where the microgrid or the smart grid is located. We must integrate also on a software level. So through communication systems, control systems, and so we should take care on during in the coding phase, and not only in the coding phase, but in the software part. And also a very important thing that must be considered is that integration, is it possible also, but must satisfy the transmission code, the regional, the national transmission code. There are countries in Europe that they have their own transmission code, and but there are also regions that have the transmission code. And if you going to install or to plug new devices or new microgrid in that scenario, then you can do that if and only if you satisfied all the standards, all the rules defined in the transmission code. So it's not that there is a unique code that is valid worldwide, but there are some slightly difference between the regions and the countries too. So when you're going to work, or when you want to integrate something in an already existing smart grid or a new smart grid in this area, you should consider not only hardware and software, that maybe it's up to the supplier, but you need also to include all the rules in the transmission code. So the integration of in smart grids, you can easily integrate and remove assets to the microgrid. That is easy because if, for instance, you have a building connected to a smart grid or to a microgrid, and then all of a sudden that building is not in use anymore, you should be able to remove that building from the smart grid. You need to follow a protocol for communication that enables interoperability, because if you are going to connect different devices and different systems, they must be able to communicate, to exchange information among them, but also with the control system, and that can be done using a standard protocol for communication. And there's also another important thing in the smart grids that maybe sometimes is not well considered, that it's not true that smart grid is made of new things and new assets. Sometimes smart grid or microgrid simply has to integrate existing platform, existing also remote control system, and existing buildings too. So you need to not only to think about the new, but also the old one. How can we interact? How can we integrate something with what is already there, what is already existing, that has and maybe an old hardware, an old software, and an old standards too. So the capabilities that are requested for integration in the smart grids is also to consider all the actors, new actors in this scenario, that are consumers and producers, new assets, and so if you want to integrate something new, maybe that is just out in the market, or maybe something that has never been connected before, so you need to do some new work, extra work from scratch, but also you need to integrate something that's already there, something already existed, that can be a platform, can be a control system, can be a SCADA, can be an already existing building. And also you really have to take care a lot on the communication part, especially in the protocol, because if it is not possible to send measures from the asset to the control system and vice versa, you cannot control, you cannot coordinate, and everything is ruined. So the communication and transmission part is very important. The microgrid that we have here in Loccioni is LEAF microgrid, and in this case, LEAF stands for Life, Energy, and Future. I will show you later on. LEAF stands also for something else, but here, besides the English word of LEAF that all of us know, it's also Life, Energy, and Future. So the microgrid that we have here in the Loccioni headquarters integrates existing assets, because there are buildings in this microgrid that were built in the 70s, in the 80s. So we integrate old assets with the renewable resources. All buildings have rooftop PV installations, and then we have also a micro hydropower plant, a new one. We have industrial buildings, and we have electric charging station, and electrical and thermal storage too. We have an EMS, energy management system, developed internally by Loccioni that controls and coordinates all these assets. And then there was a building automation in each building that takes care of lighting, shading, heating, and everything. And this microgrid is enabled for island mode. So it's enabled to have this headquarters in an resort to be completely independent from the national grid. This is the microgrid, and just a brief recap if some of you doesn't know. Okay. I think maybe some of you have the Microsoft on. Okay. So we are all talking now from the Leaf Lab on the right bottom. And then we did a micro plant of 48 kilowatt peak. All buildings have a rooftop PV rooftop installation. We have electrical and thermal storage power plant. storage system, and we have only one point of delivery with the grid. All these systems are connected in parallel. That means that if we decide tomorrow morning to unplug the Leaf Lab or the micro hydro power plant from the microgrid, we can do it easily. So that sounds also very important. The communication part, how actually it is possible to have all these assets and then send and control all of them via a website, because basically this is what we do. So you control all of this remotely from a website. How is that possible? The first level, like the bottom one, that here I put it as the first one, is the assets and level. So all the system, all the assets that are connected to the microgrid, all the meters that you have installed. This is the first level, the hardware level, let's say. This here, in this level, there are all the measurements that you are interested to control or simply to collect. Also that. It is very important in this phase that if you add or remove some meters and some measurements, you should communicate that to the EMS, because let us picture that we have we are collecting measurements from the hydropower plant, and then one day a guy decides to remove that meter. That means that on the EMS, that measurements will be zero from that day, and that can be seen as a fault. So people think that the hydro is not producing energy, but actually it's not like that. It's simply that the meters is not installed anymore. So it's not a fault. There is energy produced by the hydro power plant, but simply the measurements is not arriving, is not acquired anymore by the EMS, so cannot be controlled actually. And at the same time, if you install some new meters, so you are acquiring the new information, you should communicate that to the EMS part, because otherwise that measurement that you would like to monitor and to control, you cannot do it. How can you control something if it is not stored, if it's not sent to the control system? So that is very important. Then there is the local energy management system that is at the local level. And then there is a central EMS that is on the cloud. In our case, on the cloud, and that enables you to implement all the modules that you want based on optimization too, as we said before. So peak shaving, optimization, fault detection, everything. New one and tailored module too. You implement these modules at the central level, and you control in a way that you prefer all the assets of the microgrid. And okay, this is the framework that we have, and here you can see the LEAF doesn't mean Life Energy Future, but Lazzoni Energy Automation Framework in this case. So you can see the bottom part of the picture of the slide, assets. So that is the asset level. All the measurements from the assets are collected here. Site measures. So you have the PV rooftop installation, you have the battery, you have hydro production, you have consumptions too, because we have to monitor also the consumption. So all these assets and new one too, the measurements are collected at this level. Second level, local EMS, battery management system. These are the management strategy that are implemented at asset level, locally. And then there is the upper level, the central EMS. From the website, remotely, you can control the microgrid, you can select the control strategy that you want for the battery, for the hydro production, or you can perform a data analysis, you can integrate with the markets, you can integrate forecasting too here, and this has been developed internally by Lazzoni. So it is very, very flexible, and so modules can be exchanged from central to local very easily, and it can be accessed from web, but also from mobile, so from a tablet or from a mobile that you can have access and control the asset of the microgrid. So far, which kind of integration capabilities, let's say, which kind of knowledge has been, it is requested in this phase in the communication system? Of course, a good knowledge in ICT in information communication technology, in coding, because the framework has this structure also on cloud, so coding is very important. You need to know the hardware, so that is about the meter, so that you are installing, and also electrical and thermal equipment. You cannot measure something if you don't know how it is done, because there might be also a risk that you are going to install a meter in the wrong part of the heat pump or the wrong part of the boiler or the battery. So you need to know what you have, what you are going to monitor and to control. So these are the main competencies that are requested at this stage of the integration, that is the communication part. Then we have the control system. We need control system, we need to control all the assets and to coordinate. We can use the optimization-based controller we have seen before. We can implement a demand response. It would be at this phase of the integration. We have the EMS that has been developed internally by Loccioni. That means that we can, for instance, control the battery for peak shaving. We can use the battery for increasing self-consumption. We can go on island mode. We can use the thermal storage to store energy during weekends and use it during the weekdays. And we can also implement other control strategy, because there will be modules, and then simply including the framework that we have and run and see what happens. The control strategy, every control strategy that we can develop and we can implement need the interaction with the assets. You need to know what you're going to control. You need to forecast, because you can decide a control strategy based also on renewable production and also consumption. So you need also forecasts that are going to be crucial. And also you need integration with the market, because the main idea is still why you want to do peak shaving or increase self-consumption to minimize costs, of course. So you need to have this integration with the energy market. So these are crucial in the design of the control system, and also integrating the different parts of the control system into the smart grid. And this is a screenshot of the EMS that we have here. You can see the various building, and so in this case the storage, for instance, wasn't working. So if you see the second blue box on the bottom, there was a 0 kilowatt. The storage wasn't working at that case, but the renewable production was 76.55 kilowatt. And you could see there the overall production, because we had 33.10 kilowatts produced by the micro hydro along the river, and that we had a PV production, the orange one that you see on the other building, of 26.90 kilowatts on the leaf lab, and about free production 7.92, 2.52, 1.79 kilowatts in the other buildings, and then we had 1.79 in another PV installation that we had. Battery wasn't working, so you see the purple line, there was 0 kilowatt, and then there was the consumption. There was building was consuming 16 kilowatt, or 221 kilowatt, 126 kilowatts. So that is a global picture of consumption and production and the storage capacity, and also energy in case the battery is working, of the microgrid. And that is done by the EMS that we have in here in Loccioni. So, but this EMS, how it has been done? By integrating through communication protocols, through meters, through the hardware that we have, through the coding of transmitting all the measurements to the cloud, and by implementing the right control strategy. So all these pieces that I've mentioned so far, they lead you to have this kind of structure. And here is how we can select the control strategy that we want. When I told you that it depends on, these are simple modules. These are modules, like for instance, if you want to implement a peak shaving, you click there on peak shaving details, you set the parameters that you want, and then you implement the that control strategy. And that is simple, the screenshot from a web page. So all the assets can be controlled remotely from web. And another aspect, as also Nicholas mentioned before, is the role of aggregators. That's something that must be included in the design of control system, and this is also something that is very important in the area of integration. Imagine that we have n system in a microgrid and a smart grid. There might be a traditional production, can be consumption of a house, of companies or industries, and then we have batteries, for instance. Instead of having n number of systems, we have an equivalent system. So we aggregate all these systems into only one. That means that the EMS, the energy management system, controls the equivalent system by sending it the optimal control signal, and then it's the equivalent system that disaggregates the control signal and control all the system below. And that is a form, this is called aggregators, is a form of integration. And so this is something that must be considered because, as Nico said, it's going to be crucial and very, very important in the future. How the signal can be disaggregated, there are some merit-order strategies or distributed optimization, or also you can consider, for instance, to send the control signal to the asset that it will be less damaged. So that's also another thing that can be considered. And you can aggregate both consumption and production inside the equivalent system. But to do the aggregators as part of the control system, of course, you need knowledge and integration capability regarding the integration value system with various dynamics. So you need to know the system, you need to know the protocols, so you need to know also how to control them at the local level, and also how to aggregate them at the equivalent system. So as you can see, various capabilities that are requested. So we need to know the actuators to control the assets. We need to also know how these assets are done, so we can add some mathematical modeling competences too, also to define the optimization problem. The EMS is controlling the assets also in response to the energy market, so the energy prices, and also some data analysis and control theory, because these are models that can be implemented at central EMS level of the system. So these are some extra capabilities that are requested in the control system part of smart grid. Another aspect of integration and smart grid is the human interaction. That we cannot think to integrate things in the smart grid, but I mean, we need to integrate also people into smart grid, not only hardware and assets and batteries, production and everything, but we need to integrate people into smart grid. And that's something that must be considered, because the world for people are changing completely, the idea of energy, so we need to integrate them in this process. So which kind of competencies that will be? That will mean this involves the design, psychology, the engineering part, of course, web graphics, philosophy, architecture, data visualization also, and medicine too, related to health and everything. So an example, for instance, is in the MyLeaf that we have, that some of you has already worked on. We focused a lot on how to visualize the desired information in a proper way. So it's a data visualization, but at the same time it's also web graphics. Try to provide information in a clean and easy way, but effective. So it's this is a new aspect regarding like putting the people in the center of the smart grid, because if they are involved, if they are informed, they are going to accept easily this new scenario in the energy world. we have also this leaf meter. That was something that Lucioni has done many years ago, and the idea is to bring this pot, because maybe it's a huge pot. Now you see it was like 1.5 meters high, something like that, and it's a huge pot, and you bring it to the customer, and on that display there, the main measures are displayed. So that means that people are working there, or we have one of the 3 centers at the hospital in Ancona. So people are working there, but also people are visiting, and they can see consumption and production of the building in real time. And they're informed. They have real-time access to the energy fluxes of the microgrid of the building, and it's something that is it's something linked with design, but also how to make people more informed and more involved in this scenario. This is some work also was in Italy, the company, and what we have done, we have created a sort of path from different stations and solutions that we have provided to a customer, but we have provided a sort of path, like people are guided from one installation to another, and so they know exactly what is happening, they know why that installations are there, and they know what are the benefits of these works. So here, yes, it's the part of natural gas, and the cogeneration is still the same installation that I've mentioned you before. And this one also is this is a container that has a storage inside, a lithium storage inside, and that is for the research center north of Italy. But the idea is that while we do not provide a raw container like that, because maybe this is a research center and they have to test how a battery could work in a smart grid. So the idea is like, if it's going to work and then you're going to bring this into a real city, how people can react to a raw container like that. So it's better to make some window and some glass doors, for instance, so people could see inside, and also some LED, green LED outside, so people are like attracted by this product, and they're willing to know what is going on inside, and they're willing to accept it easily, because it's nicer than a raw container like that. Because what we need to start to think is that, for instance, storage, batteries and containers, they're going to be used more and more over the years. So we cannot think that we will have lands full of raw containers like that. And maybe we should start to think about how to make this lands of containers nicer, because otherwise people that are going not to accept it, they're not to be interested in what's going on. So they are not willing to understand if they really need this kind of battery or not. So they're really to accept this transition into new energy scenario. The same here was in Sweden, and people, for instance, here, they were not willing not to have the battery, but to have a wind farm, because the battery was connected to a wind farm, and they didn't want a wind plant on this island in Sweden. So to make people more willing to accept this, we thought, okay, instead of a container, you will have like a Swedish house. So inside there's a container, that's a marine container, simply painted red and with the roof, fancy roof and stuff like that. But in this way, people don't see a simple wind farm and a container, but they see a Swedish house with the wind farm, okay, but still they see something that is similar to what they used to see. So they can accept it easily. So to the competencies that we need, we should add design, graphics, philosophy and psychology too. You need to talk to people. You need to put the person and the people in the center of the smart grid, and make the person accept this transition, this new scenario. But as well, we need to add also methodology. So like define a standard how to proceed in the integration of all these competencies.
Thank you, Nikos, and thank you, Laura, as well. Very, very interesting presentation, both presentations. Are there any questions, please?
Yes, hello. Here is Federica from Exergy. Hello, everyone. I would like to add a question. As really interesting, both presentations were really interesting. And as I totally agree on this view of having more people, more participation in and more knowledge in terms of the smart grid. So I would like to know, do you foresee any limitation, any further limitation in the integration of the residential sector, of the smart grids in the residential sectors? Or these are the same limitations that you already found in the TUC and in the LEAF Luccioni laboratory? That's my question. Thank you.
Okay, then thanks, Fede. No, I mean, I don't think in a residential point of view there will be, I mean, what we have seen also from a customer point of view, that when they're going to install something near to a city or a small village or town, they need to talk to people. That's the main thing, because if you are going to send them a post by saying we have an issue with the battery, for instance, and what the customer did is simply sent a letter to the citizen of this very small town, very small, by saying we are going to install this one there, and that will enable to go on island mode. And the citizen, they were like, okay, we don't care. We are not going to put the battery there because we don't care about the island mode. Then they had the meeting with the mayor, and they start to discuss about the benefit of that. And all the citizens, all of them accepted the installation. So you need to inform people, you need to talk to them, and you need to provide them the right information also. For instance, many years ago, also there was an island in Denmark that was fully powered by renewable energy. And then one night there was a huge storm, and there was no electricity on the island because they stopped the wind production. They didn't have storage, and there was no electricity. And the citizens, they were really angry because they say, okay, we have wind farm. Why don't we have electricity now if it's so windy? They didn't know that you cannot run wind farm if it's too windy. So you need to inform them. You need to tell them the right information. You need to tell them advantages and disadvantages of the installation. Other limitation that no. You need only to inform them in the right way. That's all.
Thank you very much, Laura. So what's the disadvantage in this sense? Why should the residents be against the microgrids, for example? I think it's just something that will add benefit, in my point of view.
That in Sweden they were against because they didn't want that's just very it's very dark there in the winter time, and they didn't want that, so they used to have this dark forest in front of them with no light at all, and they didn't want a container with LED lights in front of them, and they didn't want a wind farm on the opposite side with only one plant, actually, on the opposite side of the wood with the red light on top. They didn't want no light at all. That was the big issue that they had. That was the big issue. That's why it was easy to find a solution, because the client put the wind farm in another place, and we didn't put the light on the container. So it was easy to find a solution. But that is, you can see that very silly situation. You know, it's not they don't want this microgrid for some issue related to earth or something. No, it's that they're used to see dark, and they want to see dark. They don't want to see any light or anything, you know. Or sometimes a person complained because he was afraid that birds could be killed by the wind plant. So they're not really important thing, you know, but you need to inform them, you know, you need to find a compromise, you need to involve them. Otherwise, if you just say, we're going to do that full stop, it's not going to work.
Perfect. Thank you very much, Laura.
Excellent, thank you. Any more questions? In this case, Laura, can I ask a basic question, please, about storage in the leaf microgrid? You refer to electrical storage and thermal storage. What is the thermal storage that you use?
So as a thermal storage, we have a sort of, sorry for the raw term, it's like, how do you call it? It's swimming pool. No, it's
a water tank, a thermal water tank.
Thank you. I was saying a swimming pool. It's not swimming. Yes, it's a water tank. Yes.
Okay, it's water for the storage. Yeah, excellent. Yeah, thank you. And another question again. You refer, and we're hearing about the mathematical modeling for that. Of course, it is used quite a lot for the optimization. But do you know, is there any research on new mathematical models to control the microgrids and the grids in general, or is it only using developed mathematical models to optimize the operation?
Usually, I mean, if there are some mathematical models for the asset that you are controlling, no? And then you merge together this model and you constrain the variables of each model to create the microgrid. A mathematical model for the entire microgrid, I don't know if it has been done. I don't know if a mathematical model for the entire grid. I don't know. What I'm used to work on was that you have a mathematical model for each asset, and then you constrain each model by adding a constraint related to all the variables. So that was what I was used to work on. But an overall model for the entire microgrid, maybe, but I'm not sure. I don't know.
Yeah, but it is the different components that they are then connected together and optimized. Okay, yeah, thank you.
Then what you do is that you can, of course, you need to constrain all the components. So you do that in the objective function because you want to minimize cost. But if you want to minimize cost, I mean, as an optimization problem. But also you constrain the variables, adding a constraint in the matrix, basically, because the constraints that you define, they simply define the mathematical model of the asset, and also they link variables, so they link the asset together. For instance, if you are using the PV production to store it in the thermal storage, that means that you need to link the model of the PV production to the model of the thermal storage. You know, that is because if they're linked in this way. So usually what I'm working on is that you have a single model for the asset, and then you merge them together in optimization model. If there's an overall model, I might say probably it is, but I don't know it. I'm not aware of it.
Thank you.
May I just add something to Laura's answer? There has been a holistic, let's say, approach, an approach on microgrid level that I have come across by Professor Kolokocha and a postgraduate student here called Mrs. Provata, and it uses a genetic algorithm optimization. I cannot describe the details of this methodology, but it's a quite interesting piece of work.
Okay, thank you very much. Thank you, Nikos. Thanks.
Thank you.
Any more questions from anybody, please? It seems not. Okay, in this case, thank you very much to Laura and Nikos for the very interesting presentations, which will be available to everybody later as well. Also, please, if you can complete the very short questionnaire. It will not take more than 2 or 3 minutes each, I think. And also, we have arranged another double webinar on the 26th of April. It's a Wednesday, I think, the same time. We'll arrange the time, but it will be in the morning. And more details will follow, but please, if you can pencil the date in your diaries, we'll send some information very soon. So, shall I give the microphone to Nikos again?
Yes, thank you very much, Professor Kolokotroni. Thank you for organizing this session. I think we can end it now. Thank you everyone for your participation.